Something is moving through the wire in the wall behind you right now. A current of electrons threading through copper, each one responding to a voltage difference the way any charge particle must, each one pushing the next, the whole chain of them sustaining the light in the room or the device in your hand. The motion is continuous, uninterrupted, governed by rules so reliable that engineers build entire civilizations on top of them. You have known about electrons since early in your education. They orbit atoms, they carry charge, they flow through conductors. The picture is comfortable, and it has been comfortable for a long time, which is exactly why it is worth pausing on, because the electron examined carefully does not behave the way matter is supposed to behave. Matter in the ordinary sense is made of things that are made of smaller things. You press into a surface and it resists because particles are there, packed together, each one a composite of deeper constituents that push back when forced close. The proton has 3 quarks inside it. The neutron has 3 quarks inside it. Every nucleus in every atom in the wall behind you is a bound system of constituents that can, under the right conditions, be probed. You can fire something at a proton hard enough to scatter off its interior. The interior is there. It responds. The structure reveals itself. Fire something at an electron with the same intent and nothing comparable happens. No internal scattering. No suggestion of hidden geometry. The electron deflects as a whole or not at all. Every experiment designed to find something inside it has returned the same answer, which is that there is no inside to find. And yet the electron has mass, it has charge, it responds to forces with perfect consistency. It is unambiguously real and unambiguously present, acting on the world with precision while carrying no interior structure that could explain how. So what kind of thing has properties without parts? What kind of entity acts on the world completely, with no mechanism hidden inside it doing the work? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, let me know in the comments. I always wonder which curiosities other people carry around with them. With that said, let's get back to the topic. The electron is not the only particle with this character. It belongs to a family, and understanding what that family is and why it exists as a distinct category in nature is where this descent begins. The word particle has been doing a lot of work for a long time, and it has been covering a gap that most introductions never stop to examine. When physicists in the early 20th century began confirming that matter was made of atoms, and that atoms had electrons around them and nuclei inside them, the word particle felt like a natural fit. Small things, discrete things, things that could be counted and tracked. The electron slotted into that language without friction, and for decades the language held well enough that the gap beneath it went largely unexamined. The gap is this. The word particle implies an object, something with a boundary, a location, an interior that in principle could be examined. When you call something a particle, you are borrowing the intuition of a grain of sand or a billiard ball, just made smaller. That intuition works for composite things. A grain of sand has an interior because it is built from atoms. A proton has an interior because it is built from quarks. The word particle, applied to these things, is carrying real structural content. There is something inside that the word is pointing toward. Applied to the electron, the word is pointing toward nothing. Every measurement ever performed on an electron has treated it as a point. No experiment has returned a radius. No scattering pattern has revealed internal constituents. Down to the smallest distances current technology can probe, which are extraordinarily small, the electron has shown no size and no structure. The word particle in this case, is a label that has outlasted the intuition it was borrowed from. This matters because the question of what a lepton is cannot be answered inside the old language. If you try to define a lepton as a certain kind of small object, you immediately run into the problem that the object has no interior to distinguish it from other small objects. The distinction has to come from somewhere else, from behaviour, from what it couples to and what it ignores, from the rules it obeys and the rules it is exempt from. The category of lepton is not a description of shape or size or composition. It is a description of how something is permitted to exist within the structure of physical law. That shift from object to permitted pattern is not a philosophical preference. It is forced by what experiments return. And once the shift is made, the question transforms. Asking what a lepton is made of stops being useful. Asking what rules define a lepton and why those rules hold is where the actual description lives. That description begins not with the electron as an object, but with the electron as an excitation of something continuous, something that exists everywhere before any particle appears at all. To understand what the electron actually is, the description has to move one layer deeper than particles. Not deeper in the sense of finding something smaller inside the electron, but deeper in the sense of changing what counts as the fundamental ingredient of the theory. In quantum field theory, the basic entities are not particles, they are fields, and the distinction between those two starting points changes everything about how the electron is understood. A field, in this context, is not a region of influence surrounding an object that already exists. It is something more primary than that. A field is defined at every point in space and time, continuously, whether anything observable is happening there or not. The electromagnetic field exists in a region of empty space with no charges nearby. The electron field exists in a region where no electron has ever been detected. These fields are not produced by particles. They are the substrate from which particles emerge. The particle is not the fundamental thing with a field attached to it. The field is the fundamental thing, and the particle is what the field looks like when it is disturbed in a specific way. What we call an electron is a localized excitation of the electron field. Energy is concentrated in a small region of that field, and that concentration propagates through space according to the rules governing how the field evolves. The excitation has mass, it has charge, it has a precise set of properties, but those properties do not come from internal components arranged inside a tiny object. They come from the structure of the field itself, from the rules written into how that field is allowed to behave, and from how it couples to every other field present in the same framework. This is not merely a restatement of the same picture in different language. It is a genuine shift in what the explanation appeals to. When you ask why the electron has the mass it has, the answer inside field theory points to the strength of the electron field's coupling to the Higgs field, which sits everywhere as a steady background. When you ask why the electron has the charge it has, the answer points to how the electron field transforms under the symmetry operations that define electromagnetism. When you ask why the electron has no color charge, the answer points to the fact that the electron field simply does not couple to the gluon field at all. None of these answers require an interior. None of them require hidden machinery doing work inside a tiny sphere. The field's identity is written into the theory at the level of the field itself, and the particle inherits that identity completely. This reframing is what makes the category of lepton possible to define precisely. A lepton is not a small object with certain properties painted onto its surface. A lepton is an excitation of a specific class of fields, fields that share a particular set of couplings and a particular set of absences. The absences are just as important as the couplings. What a lepton field does not interact with is as defining as what it does. And the most important absence, the one that separates leptons from the other great family of matter particles, is the one that determines which force the lepton is completely invisible to. That absence has a precise name, and understanding it requires going inside the force that leptons are exempt from. Inside every proton sitting in every nucleus in every atom of your body, 3 quarks are bound together by something that has no equivalent anywhere in ordinary experience. The force holding them is not gravity, which acts on mass and reaches across any distance. It is not electromagnetism, which acts on electric charge and weakens gradually with separation. It is something that operates only across distances smaller than a single proton, something that grows stronger as quarks are pulled apart rather than weaker, something whose carriers are themselves subject to the force they carry. This is the strong force, and the reason it acts on quarks and ignores electrons entirely comes down to a single property that quarks carry and leptons do not. That property is color charge. The name is borrowed loosely from the way colors of light combine, but the analogy should not be pushed. Color charge is not visual. It is not a metaphor. It is a real physical quantity, as concrete as electric charge, operating on its own axis of physical reality, entirely separate from anything electromagnetism acts on. Each quark carries one of 3 color charges labeled red, green, and blue purely by convention. The strong force, carried by particles called gluons, acts on color charge the way electromagnetism acts on electric charge. It pulls color charges together, holds them in specific combinations, and enforces rules about which configurations are permitted to exist as stable, observable objects. The rule is strict. Every stable particle that can exist independently in nature must be color neutral. 3 quarks, one carrying each color, cancel to produce a color neutral proton. A quark and an antiquark carrying opposite color charges cancel to produce a color neutral meson. The strong force does not allow isolated color charges to persist. Pull a quark away from its partners, and the energy stored in the gluon field between them grows until it is sufficient to produce a new quark-antiquark pair directly from the field itself. The original quark never escapes. It simply acquires new partners. Color confinement is total, and it is permanent. Now consider the electron field. It carries electric charge. It couples to the electromagnetic field. It responds to photons, the carriers of electromagnetism, and through that coupling it participates in every chemical bond, every reaction between atoms, every interaction that gives matter its structure at the scale of molecules and above. But the electron field carries no color charge. It does not couple to gluons. The strong force has nothing to act on when it encounters an electron. The electron passes through a region of intense color field activity, the interior of a nucleus, for instance, and the strong force registers nothing. The electron is, in the language of the strong force, completely transparent. This absence is not a gap in the electron's description. It is a feature of the field itself, written into the theory at the most fundamental level. The electron field transforms in a specific way under the symmetry operations that define the strong force, and that transformation is trivial, meaning the field simply does not participate. No coupling term connecting the electron field to the gluon field appears in the equations, because no such term is permitted by the symmetry. The absence is enforced, not accidental, and this enforced absence is the first and most defining characteristic of what it means to belong to the lepton family. Leptons are the matter particles that carry no color charge. That single structural fact separates them from quarks completely, and its consequences run through everything that follows. It is worth staying with that absence for a moment longer, because the temptation is to treat it as a negative fact, something that simply is not there, a blank space in the description that carries no further weight. But in quantum field theory, absences are not passive. They are enforced by the deepest level of structure in the theory, and the enforcement has consequences that reach far beyond the particle itself. The standard model is built on symmetry, not symmetry in the visual sense of a pattern that looks the same from different angles, but symmetry in the mathematical sense of transformations that leave the equations unchanged. The strong force is governed by a particular symmetry structure, and that structure determines which fields are allowed to couple to gluons and which are not. A field either transforms in the right way under those operations to participate in the strong interaction, or it does not. There is no middle ground. There's no partial coupling. The field either carries color charge and feels the strong force completely, or it carries no color charge and is entirely exempt. The electron field falls into the second category. When the symmetry operations of the strong force are applied to it, the field is unchanged. It transforms trivially. In the language of the mathematics, it sits in the trivial representation of the symmetry group that governs color. That phrase sounds abstract, but its physical meaning is direct. The electron field has no handle for the strong force to grip. The gluon field reaches out and finds nothing to act on. The interaction term that would connect them is not small or suppressed. It is absent from the equations entirely, forbidden by the symmetry itself. This matters because it means the lepton's exemption from the strong force is not contingent. It does not depend on the energy scale of the interaction. It does not break down under extreme conditions the way some approximate symmetries do. It is a structural feature of how the electron field is defined within the theory, and it holds at every energy scale the standard model describes. An electron inside a particle accelerator moving at a significant fraction of the speed of light, passing through regions of intense field activity, is just as exempt from the strong force as an electron drifting slowly through a copper wire at room temperature. The exemption is built into the field's identity. Consider what this means for the behavior of matter at every scale. Quarks are permanently confined because the strong force will not release them. Every attempt to separate a quark from its partners produces new bound states rather than free color charges. The entire structure of nuclear matter, the protons and neutrons that make up every nucleus, exists because the strong force locks quarks together with a confinement that is absolute. Leptons stand entirely outside that confinement. They move freely through space in a way quarks never can. They are not pulled into bound states by color interactions. They are not subject to the tube-like gluon field geometry that seals quarks inside nucleons. Their freedom of motion is a direct consequence of their structural invisibility to the strong force. This is the first layer of what lepton identity actually is. A lepton is a matter particle whose field carries no color charge, whose exemption from the strong force is enforced by symmetry, and whose freedom from color confinement is therefore absolute and permanent. Everything else that distinguishes leptons as a family builds on top of this foundation. But the foundation itself raises an immediate question. If leptons are defined by what they are exempt from, what are they actually subject to? What forces do act on them, and what does that participation reveal about the deeper structure of the family? If color charge is the absence that defines leptons, lepton number is the presence that protects them. It is a quantity the universe tracks with remarkable consistency, and understanding what it is and why it holds reveals something important about how the lepton family is held together as a category across all interactions and at every energy scale so far examined. Lepton number is simple to state. Every lepton carries a lepton number of +1. Every anti-lepton carries a lepton number of -1. Everything else, quarks, gluons, photons, the Higgs boson, carries a lepton number of 0. In any interaction that has ever been observed, the total lepton number of the particles entering the interaction equals the total lepton number of the particles leaving it. An electron can be created, but only alongside an anti-neutrino, so that the total remains balanced. A muon can decay, but only into products whose lepton numbers sum to exactly the value the muon carried going in. The ledger is always closed, every time, without exception in any experiment ever conducted. This is not a law that was derived from deeper principles and then tested. It was noticed empirically. Physicists catalogued interaction after interaction and found that certain processes simply never occurred. An electron does not spontaneously vanish. A lepton does not convert into a quark without a compensating change elsewhere. Processes that would require the total lepton number to shift are not suppressed or rare. They are entirely absent from the record. That systematic and total absence is what elevated lepton number from a pattern in the data to a conservation law with the same standing as the conservation of energy or momentum. Conservation laws in physics are connected through a deep mathematical relationship established by Emmy Noether in the early 20th century to continuous symmetries of the equations governing a system. When a quantity is conserved in every interaction, there is a symmetry responsible for enforcing it. The conservation of energy traces to the fact that the laws of physics do not change with time. The conservation of momentum traces to the fact that they do not change with position in space. Lepton number conservation points toward a symmetry under which the lepton fields can be rotated by a continuous phase without any observable consequence. That symmetry keeps the lepton number ledger closed across every interaction the Standard Model describes. What this means physically is that the universe treats leptons as a protected category. The total lepton number in any isolated system cannot change. Leptons can be created and destroyed, but only in combinations that leave the running total unaltered. A lepton appearing requires an anti-lepton appearing with it, or a lepton elsewhere disappearing to compensate. That protection is what gives the electron its absolute stability, and what makes the lepton family coherent as a category, rather than just a convenient grouping. Lepton number is the second structural pillar of what it means to be a lepton, sitting alongside color charge exemption as a defining feature enforced by the deep symmetry structure of the theory. Conservation laws do not enforce themselves through active intervention. There is no mechanism that watches each interaction and steps in to correct a violation. The enforcement is more fundamental than that. It is built into the structure of the equations before any interaction begins, and understanding how that works reveals something important about why lepton number is not just a pattern that happens to hold, but a constraint the universe is incapable of violating within the framework that governs it. The connection between symmetries and conservation laws runs through a result that sits at the foundation of theoretical physics. When the equations describing a system possess a continuous symmetry, meaning a transformation that can be applied by any amount along a smooth parameter, and that leaves the equations unchanged, a conserved quantity follows automatically. The symmetry does not produce the conservation as a secondary effect. The conservation is the symmetry, expressed in the language of measurable quantities. They are the same fact stated two different ways. For lepton number, The relevant symmetry involves the phase of the Lepton fields. A quantum field is described mathematically by a complex quantity at every point in space and time, and that quantity has a phase, an angle that can be rotated without affecting any observable outcome. If the equations remain unchanged, when all Lepton fields are simultaneously rotated by the same continuous phase, then Lepton number is conserved. The rotation is the symmetry. The conservation is its consequence. And within the standard model as currently formulated, that phase rotation leaves the equations invariant, which means the conservation holds exactly. This is why Lepton number conservation feels absolute rather than approximate. It is not a result of leptons being too heavy to decay into something lighter or too stable for any practical process to disturb. It is a result of a symmetry that is written into the field equations themselves. Processes that would violate it are not forbidden because they are energetically unfavorable. They are forbidden because no term in the Lagrangian of the standard model connects Lepton fields to non-Lepton fields in a way that would allow the total Lepton number to change. The interaction simply has no mathematical form within the theory. It cannot be written down in a way consistent with the symmetry. Consider what this means concretely. The electron is the lightest charged lepton. There is no lighter lepton for it to decay into. But even setting that aside, even imagining a hypothetical world where something lighter existed, the electron still could not decay into non-lepton particles because lepton number would not be conserved in that process. The protection is not just energetic, it is categorical. The electron's stability is not a lucky accident of it sitting at the bottom of a mass hierarchy. It is a structural consequence of the symmetry that keeps lepton number constant. That symmetry is what makes the electron permanent, and permanent electrons are what makes stable atoms possible, and stable atoms are what makes the material world as we experience it coherent and persistent across time. In 1936, a particle was detected in cosmic ray experiments that nobody had predicted and nobody immediately knew what to do with. It behaved like an electron in almost every relevant way. It carried the same electric charge. It felt no strong force. It was subject to the same electromagnetic and weak interactions. It obeyed lepton number conservation with the same precision. But it was heavier than the electron by a factor of roughly 200, and it was unstable, decaying after a short time into an electron and two neutrinos. The physicist Isidore Rabi, upon hearing about it, reportedly asked a question that captured the collective confusion of the field with unusual economy. Who ordered that? The muon, as it came to be called, was the first indication that the electron was not a unique solution to the problem of being a lepton. It was instead one member of a pattern that nobody had anticipated and that the theory of the time offered no explanation for. The muon did not fit into any gap in the existing framework. It was not predicted by any symmetry argument. It arrived as a pure empirical surprise, and it forced a reckoning with a question that has not been fully resolved since. Why does nature repeat the lepton with different mass? What makes the muon structurally significant is precisely how completely it mirrors the electron in everything except mass. It carries no color charge, establishing immediately that it belongs to the lepton family. It carries lepton number, obeying the same conservation law with the same precision. It couples to the electromagnetic field with the same strength as the electron, meaning its electric charge is identical. It couples to the weak force through the same interaction structure. If you were to write down the field equations for the muon and compare them to those for the electron, the only difference you would find is the mass term. Every coupling, every symmetry transformation, every conservation law is the same. The muon is not a different kind of lepton. It is the same kind of lepton expressed at a different mass scale. This identity in everything except mass creates a specific kind of puzzle. In quantum field theory, the properties of a field are determined by how it couples to other fields and how it transforms under the symmetries of the theory. Two fields that couple identically to every other field and transform identically under every symmetry are, in the language of the theory, the same field. The muon field and the electron field are distinct only because they have different masses, which in the framework of the Standard Model means they couple to the Higgs field with different strengths. That single numerical difference in one coupling constant is what separates the muon from the electron. Everything else is shared. The muon's instability follows directly from its mass. Because it is heavier than the electron, and because lepton number conservation permits a muon to decay into an electron, provided the other decay products carry away the remaining lepton number, the decay occurs. The muon lives for only a fraction of a second before becoming an electron, a muon neutrino, and an electron antineutrino. The lepton number balance is maintained exactly throughout. What the muon's existence establishes for the first time is that the lepton is not a singular object, but a template. And once a template exists, the question becomes how many times nature uses it. The muon arrived as a surprise. The tau arrived as a confirmation of something that was beginning to look deliberate. By the time it was detected in the mid-1970s at the Stanford Linear Accelerator Center, the theoretical landscape had shifted enough that its existence, while not precisely predicted, fit into a pattern that physicists were already beginning to suspect. The lepton was not a singular object and was not a pair. It was the first entry in a sequence, and the tau was the third entry completing a structure that now demanded explanation rather than just documentation. The tau carries the same electric charge as the electron and the muon. It carries no color charge, placing it immediately within the lepton family. It obeys lepton number conservation with the same precision as its lighter relatives. It couples to the electromagnetic field and the weak force through interaction structures identical to those governing the electron and muon. Written into the equations of the Standard Model, the tau field is distinguished from the electron field and the muon field by exactly one thing. Its coupling to the Higgs field is stronger, which means the background magnitude of the Higgs field generates a larger mass term for it. The tau is approximately 17 times heavier than the muon, and approximately 3,500 times heavier than the electron. That mass difference is the entire difference. In every other structural respect, the three fields are identical. The tau is unstable in the same way the muon is unstable, and for the same reason. It sits above the electron and muon in the mass hierarchy, and lepton number conservation permits it to decay into lighter leptons provided the accompanying particles carry the balance correctly. Its lifetime is shorter than the muons because the larger mass difference opens more decay channels and makes the transition energetically easier. The tau decays so quickly that it was initially difficult to study directly. Its existence was inferred from the precise accounting of energy, momentum, and lepton number in the debris of high-energy collisions before its properties could be measured with the detail available for the electron and muon. What the tau establishes, alongside the muon, is that the lepton template is used exactly 3 times. 3 charged leptons, each one a copy of the same field structure at a different mass scale, each one invisible to the strong force, each one carrying the same electric charge, each one obeying the same conservation laws with the same precision. The only variable across all 3 is the strength of their coupling to the Higgs field, which is to say, their mass. Nature has taken one blueprint and instantiated it 3 times, at masses that span 4 orders of magnitude, with no obvious reason emerging from within the Standard Model for why 3 copies exist, or why they are spaced the way they are. This repetition is what forces the generation question into the open. The electron, muon, and tau are not 3 different kinds of lepton. They are 3 generations of the same kind of lepton, and each charged lepton, it turns out, comes paired with a neutral partner that shares its generation while carrying almost none of its interactions. That partner is the neutrino, and its existence adds a second column to the lepton family that deepens every question the charged leptons have already raised. The charged leptons do not stand alone in their generations. Each one comes paired with a neutral partner, and that pairing is not incidental. It is structural, enforced by the same symmetry framework that governs the weak force, the one interaction that leptons do participate in alongside electromagnetism. The electron pairs with the electron neutrino, the muon pairs with the muon neutrino, the tau pairs with the tau neutrino. 3 generations of charged leptons, 3 corresponding neutrinos, 6 lepton fields in total, arranged in pairs that the weak force treats as partners. This pairing reveals something important about how the lepton family is organized within the standard model. The weak force does not act on leptons as isolated individuals. It acts on doublets, pairs of fields that transform into each other under the symmetry operations governing the weak interaction. Within each doublet, the charged lepton and its neutrino are connected. The weak force can convert one into the other. An electron can emit a particle of the weak force and become an electron neutrino. A muon neutrino can absorb a particle of the weak force and become a muon. These transitions respect the pairing strictly. An electron does not transform into a muon neutrino. The generational boundary holds. That boundary introduces a refinement of lepton number into something more specific. Beyond the total lepton number that counts all leptons equally, each generation carries its own flavor lepton number. Electron flavor lepton number counts electrons and electron neutrinos. Muon flavor lepton number counts muons and muon neutrinos. Tau flavor lepton number counts tau leptons and tau neutrinos. In the interactions described by the standard model, each flavor lepton number is conserved independently. A muon decays into a muon neutrino, an electron, and an electron antineutrino. The muon flavor number enters as +1 and exits as +1, carried by the muon neutrino. The electron flavor number enters as 0 and exits as 0, the electron and electron antineutrino cancelling. Every flavor ledger closes separately. The existence of 3 generations, and only 3, is one of the more precisely established facts in particle physics. Measurements of how the weak force carrier known as the Z boson decays constrain the number of light neutrino species with extraordinary precision. The Z boson can decay into a neutrino-antineutrino pair, and the rate at which it does so depends directly on how many neutrino species are available. The measured decay rate is consistent with exactly 3 light neutrino species, and inconsistent with 4. The universe has been counted, and the answer is 3 generations of leptons, no more. What the standard model cannot explain is why 3. The equations accommodate any number of generations. Nothing in the symmetry structure demands 3 rather than 2 or 4 or 17. The number 3 is an input taken from experiment, not an output derived from deeper principle. The 3 generations of leptons sit in the theory as an observed fact without an explanation, one of several places where the standard model describes the universe with precision while remaining silent about why the universe is arranged the way it is. That silence is not a failure of the theory so much as a boundary it has reached, a place where description ends and deeper questions begin. And those deeper questions become most acute when attention turns from the charged leptons to their neutral partners, whose properties strain the Standard Model's framework in ways the charged leptons never did. Every second, approximately 100 billion neutrinos pass through each square centimetre of your body. They arrive primarily from the Sun, produced in the nuclear reactions that power it, and they pass through you the way light passes through glass, except far more completely. Glass stops some light. Your body stops almost none of the neutrinos passing through it. The Earth itself is nearly transparent to them. A neutrino travelling through solid lead would need a column of it several light years thick before the odds of a single interaction reached 50%. This is not an approximation. It is a precise consequence of how weakly the neutrino field couples to everything else. The neutrino carries no electric charge, so it does not couple to the electromagnetic field. It carries no color charge, so the strong force is equally blind to it. The only fundamental force that acts on a neutrino is the weak force. And the weak force, at the low energies characterizing most neutrinos produced in stars and reactors, is extraordinarily feeble. Gravity acts on neutrinos as well, but at the scale of individual particles it contributes nothing meaningful to any interaction on human timescales. What remains when both color charge and electric charge are absent is a particle that exists almost entirely outside the web of interactions that makes matter tangible. The charged leptons are at least visible to electromagnetism. They participate in chemistry, get deflected by magnetic fields, and leave ionization trails in detectors. The neutrino does none of this. Its only window into detectability is the weak force, and that window is so narrow that detecting neutrinos requires either an enormous detector, an extraordinarily intense source, or both. The first direct detection did not occur until 1956, more than 2 decades after Wolfgang Pauli first proposed the neutrino's existence in 1930. Pauli introduced it as a theoretical necessity, a particle that had to exist to account for energy and momentum, appearing to vanish in certain radioactive decays. He was reportedly reluctant, writing that he had done a terrible thing by postulating a particle that could not be detected. The gap between prediction and confirmation reflects precisely how weakly it interacts. That weakness is structural, not contingent. It follows directly from the neutrino field carrying no charge under electromagnetism or the strong force, leaving it coupled only to the weak force through its generational pairing with the charged lepton. The neutrino is the lepton taken to its logical extreme, so thoroughly exempt from interaction that its passage through matter leaves almost no trace at all. For decades after the neutrino was confirmed to exist, the Standard Model treated it as massless. This was not an oversight. It was a deliberate feature of the theory's construction. The mathematical structure describing neutrinos was built around the assumption that they travel at the speed of light, that they have no coupling to the Higgs field, and that their left-handed and right-handed components are not paired in the way that generates mass for the charged leptons. The massless neutrino was not a placeholder waiting to be corrected. It was written into the framework as a precise statement about the neutrino field's identity. Then the experiments disagreed. Through a series of observations culminating in results from the Super Kamiokande detector in Japan in 1998, and confirmed by several independent experiments in the years that followed, physicists established that neutrinos oscillate. A neutrino produced as an electron neutrino, the partner of the electron, does not remain an electron neutrino as it travels. Over distance it transitions into a muon neutrino or a tau neutrino, and then back, cycling through the 3 flavors in a pattern that depends on the distance traveled and the energy carried. This behavior has a precise name. It is called neutrino oscillation, and its occurrence is only possible if the neutrino mass eigenstates, the states with definite mass, are not identical to the flavor eigenstates, the states with definite weak interaction identity. The significance of that distinction takes a moment to absorb. The electron neutrino that the weak force produces is not a particle with a single definite mass. It is a quantum superposition of three mass states, each carrying a slightly different mass, each evolving at a slightly different rate as the neutrino propagates through space. Because the three mass states evolve differently, their superposition shifts over time, and the flavor identity of the neutrino, which flavor it will appear to be when it next interacts, rotates accordingly. For this to happen, the three mass states must actually be different from one another. They must have different masses, and that means neutrinos cannot all be massless. This result cracked something fundamental in the Standard Model's description of leptons. The theory as originally constructed has no mechanism for generating neutrino mass. The Higgs field generates mass for the charged leptons through coupling terms that pair left-handed and right-handed field components. For those terms to exist, both components must be present. For the charged leptons, they are. For neutrinos in the original Standard Model, only left-handed components appear. There is no right-handed neutrino field written into the theory, which means there is no standard Higgs coupling available to give neutrinos mass, which means neutrino mass requires either adding new fields to the theory or introducing a different kind of mass term altogether. The masses themselves are extraordinarily small, far smaller than any other known massive particle. The exact values are not yet measured precisely, only their differences, but they are not zero, and that non-zero value sits outside the boundary of what the Standard Model in its original form can accommodate. The neutrino is the point where the lepton family quietly exceeds the framework built to describe it. The conservation of individual lepton flavor, the rule that electron number, muon number, and tau number each close their own ledger separately, held without exception for decades. It was treated as a firm boundary within the Standard Model, each generation sealed from the others in its own conserved quantity. Neutrino oscillation broke that assumption quietly but completely, and the consequences of that breaking reach further than the neutrino sector alone. When an electron neutrino travels and arrives as a muon neutrino, electron flavor lepton number has decreased by 1 and muon flavor lepton number has increased by 1. Total lepton number remains intact, but the individual flavor numbers have shifted. The generational boundary, which seemed structural and absolute, turned out to be approximate. It holds well enough for charged leptons under ordinary conditions, but for neutrinos it fails over any significant distance. Flavor identity is not a permanent label attached to the particle at the moment of its creation. It is a temporary condition that evolves continuously during propagation, driven by the interference between mass states that travel at slightly different rates and drift in and out of phase as distance accumulates. This matters beyond the neutrino sector because it opens something the original Standard Model had treated as permanently closed. If lepton flavor is not strictly conserved, processes involving charged leptons that change generation become theoretically possible, even if suppressed to an extraordinary degree. A muon decaying into an electron and a photon would violate muon flavor conservation. Such decays have never been observed, and experimental searches have placed some of the tightest upper limits in all of particle physics on their rate. But the strict categorical prohibition is gone in principle. The three generations are not hermetically sealed from one another. They communicate at the quantum level through the mixing that neutrino mass makes inevitable. What this reveals about leptons as a category is that the generational structure has internal geometry that a simple list of 6 fields does not capture. The fields that the weak force acts on, the flavor eigenstates, are quantum mixtures of the fields that propagate freely through space, the mass eigenstates. Those 2 sets of states do not coincide, and the angles describing how they overlap are real measurable parameters sitting in the theory as inputs without explanation. The generation labels remain meaningful, but they describe interaction identity rather than propagation identity, and the difference between those 2 things is where the internal structure of the lepton family lives. Strip away everything contingent about a lepton, and what remains is a small set of numbers. Not numbers describing its size or its internal arrangement, or the positions of constituents inside it. Numbers describing how it is permitted to behave within the structure of physical law. Those numbers are called quantum numbers, and for leptons they constitute the entire description. There is nothing underneath them that the numbers are summarizing. They are not symptoms of hidden structure. They are the structure. An electron is completely characterized by a handful of such quantities. Its electric charge is -1 in units where the proton carries +1. Its spin is 1/2, meaning it belongs to the class of fields whose excitations obey the exclusion principle that gives matter its solidity. Its lepton number is +1. Its mass is fixed by the strength of its coupling to the Higgs field. Its color charge is absent, which is itself a quantum number, the trivial representation under the symmetry governing the strong force. That list is complete. Every measurable property of every electron ever detected follows from those entries. Nothing is left over. Nothing is unaccounted for. This completeness is what makes leptons elementary, in the precise sense the word carries in quantum field theory. Elementary does not mean very small. It means that the particle's identity is exhausted by its quantum numbers, with no further internal story required to explain why it has them. A proton is not elementary in this sense because its properties emerge from the arrangement and interactions of its constituent quarks. The electron's properties do not emerge from anything. They are imposed directly by the field's place within the symmetry structure of the theory. What quantum numbers actually are, at the deepest level the standard model reaches, is a description of how a field transforms under the symmetry operations governing each interaction. Electric charge describes transformation under the symmetry of electromagnetism. Color charge describes transformation under the symmetry of the strong force. The trivial transformation of lepton fields under that second symmetry is what color charge absence means precisely. Each number is a statement about a symmetry, and each symmetry is a statement about what the universe treats as equivalent. Lepton identity is therefore not a list of properties a particle happens to possess. It is a map of the symmetries the particle's field respects, and the symmetries it does not participate in at all. Pick up a stone and feel its weight settle into your palm. That resistance, that sense of something pushing back against your hand, comes ultimately from electrons. The electrons in the atoms of the stone repel the electrons in the atoms of your skin, and the repulsion is what solid contact actually is. At the deepest level ordinary chemistry reaches, the electron is doing real physical work in that moment. It is the reason the stone does not pass through your hand. And yet the thing doing all of that work, the thing responsible for the solidity of every object you have ever touched, has no interior, no parts pushing against each other inside it, no hidden mechanism coordinating its behavior. The electron acts on the world with complete effectiveness, while being, in the precise technical sense, empty of structure. This is not a provisional statement waiting to be overturned by a more powerful accelerator. The upper bound on the electron's radius established through decades of increasingly precise scattering experiments, sits at around 1/1000th of a femtometer. A femtometer is already 1/millionth of a billionth of a meter, a scale so far below ordinary experience that no analogy captures it honestly. At that scale and below, the electron has shown nothing, no edges, no internal scattering, no constituents deflecting incoming probes at angles that would betray hidden geometry. The experiments designed to find structure have instead placed an ever-tightening constraint on how small any structure would have to be, and that constraint has reached a point where the standard model treats the electron as a mathematical point without any remaining practical qualification. What fills the space where internal structure would normally sit is something different. The electron's properties are not produced by components arranged inside it. They are inherited directly from the field it is an excitation of. The electron field has a specific transformation character under the symmetry of electromagnetism, and that character is what electric charge is. It has a trivial transformation under the symmetry of the strong force, and that is what color charge absence is. It couples to the Higgs field with a specific strength, and that coupling is what electron mass is. None of these require an interior. They require only that the field occupy its particular place within the symmetry structure of the theory, and that place is fully specified without appealing to anything smaller. This is where the lepton, as a category, reaches its flaw. You cannot ask what the electron is made of in the way you ask what a proton is made of, because the question assumes an interior that experiments have ruled out, and the theory does not contain. The electron is not made of anything in the compositional sense. It is an excitation of a field whose identity is written entirely in its quantum numbers, and those numbers are complete. A complete description with no remainder is what elementary means in quantum field theory, and every lepton from the electron to the tau neutrino satisfies that definition fully. The family is not a collection of small objects. It is a collection of field excitations whose properties are imposed by symmetry rather than assembled from parts, and that imposition leaves nothing inside to find. There is a habit of mind that physics education instills early, and that serves well for a long time. When you want to understand something, you open it, you find what is inside. You name the parts and describe how they fit together, and that description is the understanding. It works for molecules because molecules are made of atoms. It works for atoms because atoms are made of nuclei and electrons. It works for nuclei because nuclei are made of protons and neutrons, and those are made of quarks. The habit is so consistently rewarded that it begins to feel like the only direction understanding can move. Always inward, always toward smaller pieces, always toward the next layer waiting to be opened. The lepton is where that habit reaches a wall, not because the instruments are insufficiently precise, and not because the next layer is simply too small to have reached yet, but because the framework that describes leptons with extraordinary accuracy, confirmed across decades of experiment at energies spanning many orders of magnitude, contains no interior for them. The electron field is defined at every point in space. Its excitations carry charge and mass and spin and lepton number. Every one of those properties is fixed by the field's place within the symmetry structure of the standard model. None of them point inward toward hidden components doing the work. The description is complete without an interior, and completeness without an interior means the interior is not there to find. What replaces composition as the explanatory foundation is permission. A lepton exists because the universe permits a specific kind of field excitation to occur. That permission is not arbitrary. It is constrained by the symmetry structure of the theory, by which couplings are allowed and which are forbidden, by which conservation laws hold and which quantum numbers must balance. The electron does not exist because pieces were assembled into it. It exists because the conditions defined by the electromagnetic field, the weak force, the Higgs field, and the absence of any coupling to the strong force jointly allow an excitation of that precise character to propagate stably through space. The permission is the explanation. Nothing further is required. Consider what that means for the Lepton family as a whole. 6 fields, 3 charged leptons carrying identical structure at different mass scales, their masses set by 3 different coupling strengths to the same Higgs background, 3 neutrinos paired with them by the weak force, nearly massless, exempt from every interaction except the weakest one, oscillating between generations because their mass eigenstates and flavor eigenstates do not coincide. All 6 carrying lepton number, none carrying color charge, the entire family defined not by what it is built from, but by what it is allowed to do and what it is structurally forbidden from doing. That definition is quiet, and it is precise, and it is, within the standard model, complete. The open questions that remain, why 3 generations, why those particular masses, why neutrinos have mass at all, and where that mass comes from, are not gaps in the lepton's description. They are gaps in the theory's ability to explain its own inputs. The lepton is fully described. The framework that describes it is not fully explained. And that distinction between a complete description and a complete explanation is where the Lepton family currently sits, at the edge of what quantum physics can say with confidence, pointing quietly towards structure that no experiment has yet reached.